So hope you had a good fall break. I haven't gotten to grade the test yet, but it should be sometime around next week when we get your scores back, and then we can go over it and discuss from there. But today I am going to talk about. Today we're going to start talking about probability. So for the first, I guess, third of the class, we kind of covered a hodgepodge of topics, mostly less kind of math focused in general. But for these kind of ones, we'll be going over probability, more of the inference and statistical testing side of statistics. And so, who here has heard of the word probability before? Has just a raise of hands, heard it used in a saying, or maybe they've used it at some point. And so sometimes you'll hear about probability like heads or tails. So usually they do this with the quarter at NFL games. They do a type of coin to determine who receives the ball, who kicks it off, that type of thing, what side of end zone. And so can anybody tell me what the probability of a heads is for one coin flip? Yeah, 50-50, right? So a fair coin, actually with these coins in general, sometimes are more weighted on the tail side, and so the actual proportion that we found out is like 50.5% for tails and 49.5% for heads. But essentially this is one example of probability where I flip it up, I call it, and it's tails. And so this is a realization of a probability here. And so with probability comes this idea of randomness. So can you tell me exactly what I'm going to get from this coin flip if I tell you in advance? So like, can you predict that I'm going to get tails 3 times in a row if I do it 3 times? No, right. It's unlikely. There's only, 1/2 times 1/2 times 1/2 is 1/8. And so that's why these probabilities are independent, meaning, if I flip a coin, I do it once and it's tails. The next time I'm flipping the coin again, the effect of me doing it the first time has no effect on the second coin flip. And so one example of randomness is that the outcome is unknown in advance. So like doing a coin flip, you don't know what it's going to be. Another type of randomness is where a consistent pattern emerges. And then a third type is through a large number of independent repetitions or trials. So if you're just trying to figure out randomness, and I get a coin, and I go, well, it's heads, 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 heads. And I do this 7 times. Well, here is a pattern being brought up. And so I'm more likely to think that I have a biased coin towards head here because this probability is 1/2 to the 7th, which is a pretty low chance of that actually happening. And 3 is through a large number of independent repetitions or trials. And so I could continue this for however long I wanted to, as long as I have the time to do it. And so independent repetitions or trials, the outcome of one doesn't affect the outcome of the others. And so if we're talking about the example of possibly eating food, suppose I eat vegetables and then I eat protein. And then I eat protein again. And then after that I'm too full, so I just keep on eating vegetables after that. And this occasion, what I've eaten before, like my current chance to eat something, is going to have an effect on this compared to if I just do a coin flip. Me getting heads all these times doesn't influence my next chance of getting heads. And so what really is probability? I have a dice up here. You may experience probability in all different types of games, like Monopoly Life, where you have to spin that little spinner and you get a number between 1 and 10. That's probability right there. And so probability is structured randomness. It's a standardized measure of random chance. And so structured randomness, like what we have with the coin, the structured part is that we know that there's about a 50% chance of getting heads or tails. And so the structured part is what we know about the coin. What we also have is the likelihood of any event happening, and we see probabilities pop up like this. So when we talked about proportions, we can also reflect this in a proportion where this is 7 out of 7 heads, 7 out of 7 heads, which is 100%, or 1.00. And we have 0 out of 7 tails, which is 0%, or 0.00. Now, if I did this a whole bunch of times and I got, let's just say, 4 heads and 6 tails, then the proportions for this would be 4 out of 10 and 6 out of 10. Since if I have 4 heads and 6 tails, I've flipped the coin 10 times. So I now have 4 out of 10 and 6 out of 10. These are translated to decimals of 0.4 and 0.6. And so in essence, it's a range of values from 0 to 1 and are reported as a decimal. So if somebody tells you they have a proportion of 1.5 in probability, don't believe them because that's not possible. You cannot have, where we have a proportion where it's number of trials on the denominator, and we have number of occurrences of something, like heads or tails. You cannot have the number of occurrences exceed the number of trials that you're doing this for. And so the closer the probability is to 1, the more likely the event is to occur. And so if I have a probability around 100% or 1, that means his heads is very likely to appear. And so let's just get a real definition of probability. So it's the statistical experiment, observation, trial, repetition, and so on. And so it's any statistical test that results in a definite outcome. And so, like in the heads and tails, this would be the definite outcome. And so can anybody think of any examples where they've seen probability? Maybe with playing cards before, where you might think about poker and you're trying to pull out a specific card from the deck. And if you're playing 5-card poker, you get 5 cards out of 52. And then there's a chance that these are either a 2 to ace. And then you have a chance that it's either a spade, a heart, a club, or a diamond from that. And so here are just some examples of where we see probability in our daily life. So rolling a 6-sided die. When you roll out a die, like you would a Monopoly or anything else like that, you don't know what it's going to be in advance. And so there's an equal chance of getting either 1, 2, 3, 4, 5, or 6. Choosing a card from a deck of 52 cards, unless you're a magician where you already know the outcome in advance and if you already rigged the deck or something like that, you don't know what card you're going to get. Choosing an M&M from a bag, you can also think about this like if you have like a lottery system, right? Where if you have 100 names in a bowl and you shake them up and pull one out, that's an example of probability because each name is, in this case, equally chosen for here. Drug trials, educational interventions, surveys, all these show examples of probability in our daily life. But underneath all this probability is the idea of the sample space. And so the sample space is a statistical term to refer to the set of all possible outcomes. And so for a 6-sided die, if you're rolling it once, the sample space is 1, 2, 3, 4, 5, and 6. And so put some examples up here. So if I'm rolling two dice, whatever that's called, I can get 1 to 6 on the first one and 1 to 6 on the next. And so the sample space, if I add these together, if I'm doing a typical roll in Monopoly, my sample space is 2, 3, 4, all the way to 12. However, in this case, you're not equally likely to get a 2 as you are to get a 12 on them. Actually, a 2 as you are to get maybe like a 7 on a particular roll. And so what would the probability of the sample space be, of observing everything in the sample space? Well, it would be 1, the probability of sample space, because you can't get anything else other than this. If I'm rolling 2 die, and they're only 6-sided die, I guarantee you I'm not going to get anything greater than a 12, and I guarantee you I'm not going to get anything less than a 1 in this case. And so the probability of the whole sample space is 1. And so this is just here when you go back and review and go through things. I've talked about the sample space, so collection of unique, non-overlapping possible outcomes of random circumstance. So I'm not saying in this sample space, well, we could have 2, 3, 4, 5, 6. So in this case, this can only be achieved by getting a 1 and a 1. However, with 3, I can get 1 and then a 2 on the second die, or I can get a 2 and then a 1. With 4, I can get 1 and 3, 3, 1, and 2 and 2. For this, and so on. And so these do not overlap in this case. I'm not going to have like 3.5 or anything. All of these are unique events, all of these numbers. And a simple event is one outcome in the sample space. And so when I talk about a simple event, I'm talking about getting a 7 in this case, for example. A compound event is an event that includes 2 or more simple events. So if I wanted to see, I go on Monopoly and I don't want to land on my opponent's spaces, I need something larger or equal to a 10. I'm going to have the compound event of 10 through 12. And then an event is a collection of 1 or more simple events in the sample space, written A, B, C, and so on. That's just general notation of what we'll use for that. So it could be that, this is A, and the probability of A is some number between 0 and 1. And then I have probability of B is somewhere between 0 and 1. And in this case, because you can't get a 7 and these together at the same time, this probability is 0. And so we're showing more of these using and here's named as intersection. Yes?
Is there a way to figure out how many potential outcomes there could be without writing them all out?
So writing them all out is one way to think about it. But if you're doing it in the typical die case, usually these problems will just, if you know a simple case, you can extend beyond that as well and figure out what the probabilities are of.
But there's no mathematical way to figure out you do 1, 3, all these different combinations.
No, we'll take a look at when we talk about conditional probability. There will be a tree that we can write up to see all these outcomes, but to know all of these is good. So essentially, you probably will have to write out most of the events happening. But if you see here, there's a trend going across, and in the opposite way, the probability of 2 is the same probability as 12, because it's only 1 and 1. This is only 6 and 6. So the probability of a 2 is 1 out of 36. A probability of 12 is also 1 out of 36. So you can look for tricks like that. Any other questions? Yeah.
What's the difference between a compound event and just an event?
So a compound event is simple events combined together. So a simple event, if I'm talking about like the addition of 2 die, is just having, you know, one particular number here. If the number is
an event and it's a compound event. Because the definitions seem like kind of the same.
right. So it's kind of like you have an event, and then you can have classifications of events. So if I talked about like a categorical variable, there's a nominal and ordinal. There's just different types of events that can be categorized. It just depends on what your setup is in that case, or what is in the question. And so one example of this is days a week drinking. So if I get a random sample of college students, and then I ask them, well, how many days do you drink alcohol in a typical week? So since I'm asking about days, you can only have separate days in this. And so a simple event would be any one of these days. So we have anywhere between 0, 1, 2, 3, 4, 5, 6, and 7 days. How you can think about it. And so one particular event, 4 or more, is a type of compound event, where it's accumulating all of these days together. So when you guys wrote up those surveys for one of the in-class assignments, you have one of these like age categories, right? Where we would have, you know, less than 18, 18 to 25, all the way to, you know, maybe 79 plus. We'll just use that. Now in this case, one of these events would be a particular age, and then each one of these is a compound. Does that make sense? Does anybody have any questions? I think it's helpful if we take a look at it in terms of like a Venn diagram case. So I'll also write this on the board too. Where the sample space, you can think about it as all of my outcomes live within S. But I have events A, B, and C. So we know probability of S is 1. And so in this case, I have probability A right here. And then I have C, and then B right here, where they may have some sort of common intersection together. And so if we're just trying to think about this like area, you know, if you're trying to think about it like, maybe I could use like a Squid Game type of, have you guys seen that out here? Essentially, the second one, they have to take a piece of honeycomb and cut something out of it. And so that's what you can think about for the sample space here, is that the probability of an event is less than the area of the sample space. And so whatever much area this applies is whatever the probability of A is. And so in this case, A doesn't have anything to do with B and C, but B and C have some common ground between them in terms of these events. And so if you're thinking about probability and want to map it up, you can draw something like this, where, you know, I could have something, I'll just Alright. And so just getting down to the notation of probability here, P of A, and I've just said it the first way, so PA is the probability of event A happening, or we just call it P of A. A is really any event, so it can be a single event or it could be a compound event that you're talking about. But it's an outcome or collection of outcomes in a statistical experiment or trial. And so what do you think will happen if P of A is 1 in this case? I mean, we just think about it in this case. What if P of A was 1? what would happen in this drawing here? Well, it filled the whole space, right? If I have P of A is 1, that means P of S is 1. That means the only event in the sample space is A. And so you get a scenario where you have an outline of S here, and A would be right over top of these lines to the A. And so A is certain to occur, and this is one-element determinism. If I had a biased coin that every single time would land on heads, then the probability of heads would be 1, and we know it's certain to occur. If probability of A is 0, then A will absolutely not occur. And so we have that here. And so when we apply it to these simple events, we have to think about different conditions when we talk about probabilities. And so each probability has to be between 0 and 1. And so I can't have it where I have A out here, and A would be that big. That doesn't make any sense. You can't have anything larger than the sample space. And so each one of these probabilities, like probability of A, have to be between 0 and 1. So you can have probability of 0, you can have probability 1, and anything in between. And the second one is that the sum of all probabilities over the simple events is 1. So if I were to add up all the probabilities of adding 2 die together, I would get 1, because you cannot get, a 1 or a 13 here and so on. And so if you have equally likely simple events, like a typical coin, heads and tails, there would be 2 simple events. You can either get a heads or a tails. And so since they are all equally likely, both heads and tails doing it once, the probability of 1 is 1 over k, or in this case, since k is 2, it would be 1/2. I think this will start to make more sense when we go through more examples and that type of thing. It's kind of hard to talk about probability just in the abstract, but we'll go with this here. So we want to talk about lottery event probabilities. So how many of you guys have actually done a scratch off before? You've done a Powerball, anything like that? I won recently at the lottery. I won $5 from a scratch off. I'm a big winner here. And so where they get at you in this is that the lottery is pretty much, you're just donating to whatever they're supplying. Most of it's like nursing homes or senior care in the state, because you have such a low chance of winning. But in this case, we're going to talk about lottery event probabilities. So the circumstance or type of random happening that we're talking about is that a 3-digit lottery number is selected. So I'm going to erase this up here, just so we're... So we have a 3-digit lottery ticket. We have this here, here, and here. And any of these numbers can be between 0 and 9. And so the sample space is 1,000 simple events, because if you think about it, getting a chance of any one of these numbers is 1 out of 10, 1 out of 10, and 1 out of 10. Meaning you're going to have 1 out of 10 to the third chance, which is 1 out of 1,000. And so any one of these numbers can be 0 to 9. There's no influence on one or next to it. And so the probabilities for any of these simple events being 0, 0, 0 to 9, 9, 9 is that 1 out of 1,000 chance. And you're assuming that these are all equally likely. If for some reason they were pulling these single-digit balls out of a system to make the number, and the pulling guy had an agenda, then that wouldn't be classified as all equally likely of happening. And so what if you just want to find the last digits of 9? And what you could do like I was saying, you could do all the different outcomes for this to figure out the probability, but then you'd be counting 100 different one of them, and you wouldn't want to do that. And so one way you could do this here, this goes 0, 0, 9, 0, 1, 9, all the way to 9, 9, 9. But one way of doing this quickly is that if you figure out just a smaller pattern of what's going on. So this is what helps in probability and statistics in general, is finding these patterns. And so I go 0, 0, 9, 0, 1, 9, 0, 2, 9. I'm thinking, okay, well this is 1, 2, 3, and this can go to all the way to 0, 9, 9. And so out of these, I have 10 occurrences. And since the first number can be unique for 10 different times, I would just multiply this by 10 and get 100. And so you know there's 100 possibilities out of 1,000. And so the chance for that particular event is 0.1, or 10%. If you want to have all 3 digits being the same, you know, this is just an easy one to map out since there's only 10 of them. It would be 1 out of 1,000 since they all need to be exactly the same. Does anybody else have any more questions before I move on to talking about event complements? All right. So complement of an event. So this isn't the typical type of like, hey, you look nice today. It's not that type of compliment. It's with an E in here. It's talking about the event that doesn't happen. So if we go back to that particular picture, where I'm talking about this being the sample space, and this little black circle is A, all of this space out here is not A. So this part is a complement, meaning all of the events that are not A. So just think about it as the opposite of the event A occurring. And kind of like what I draw here, you have event A, and once you have the probability of event A, you can figure out what the event of not A is. And so how do we compute it? Well, all we do to calculate P of AC, since we know, if we take a look at this drawing right here, we have the probability of S is 1, and let's just say the probability of A, for this example, is 2.25. I know it doesn't look exactly right, but let's roll with it. And so for this case, in order to figure out P of AC, we know that P of A plus probability of AC equals 1. Because we have all the things that are A and all the things that are in the sample space that are not A to equal 1. And so all we need to do is plug in these numbers here, and you have the probability of A complement is 0.75 or 3/4. And again, all you have to do for that is 1 minus the probability of A. So that's the idea of complements of events. I'm also going to introduce the idea of independence and dependence. And so 2 events, A or B, are independent of one another if the outcome of one event doesn't affect the probability that the other one will occur. And so some examples of independence are the head toss, or rolling of one die with the other if you don't bump into the other die, and then that might affect what's going on. If you roll in 2 separate boxes or something, that would be independence. And so example of this is that we have event A. So A is that you draw a 5 from a 52 card deck. And event B is drawing a 5 from the same 52 card deck. So you're doing A and then you do B. Well, what's the probability A? Well, if you drew a 5 on the first draw and you don't replace it, the probability of B is what? It's lower because if you think about it, using this card concept, the probability of A is just 4 out of 52 because you can have a 5 and then all the different suits of it. And so if I take that 5 out, then the probability of B, I don't have 4 cards anymore that are 5s, I only have 3. And so because I've taken away, I have to take away from the denominator. And so in this case, we have a lower number. I believe this is 1 out of 18. This is 1 out of 13. Yeah, thank you. And so the probability of A is more likely to happen than the probability of B in this case, and they depend on each other. Now, if you replaced it, if you replace the card in the deck, you're going to have the same probability for both, since you still have the same number of cards in each deck. It would be like if you're selecting a card from 2 different decks that are exactly the same. And so if you didn't draw a 5 and replace it, so that's if you did. And then if you didn't, the probability of B, so didn't draw, the probability of B would be 4 out of 51 in that case. And now, of course, we know 4 out of 51 is greater than 4 out of 52. And so you have a higher chance of drawing a 5 if you knew that that first card wasn't a 5. If you don't replace it, are events A and B independent or dependent? What do you guys think? If you just leave that card out, dependent, right? Because these probabilities change if you draw that particular 5 out. But if you do replace that first card, then events A and B are independent, right? And so one example here is winning a free lunch. So you put a business card into a glass bowl. I'm sure you guys have seen this even at businesses around town where they have a little section for business cards, and perhaps they're just drawing for a free lunch. And you and your friend Vanessa put in a card in 2 consecutive weeks. And so the different events are, A, you win in week 1, B, Vanessa wins in week 1, or C, Vanessa wins in week 2. And so A and B, they refer to the same type of event because you're talking about week 1. And so the same circumstance happening here is talking about week 1 and week 2. And so since they're referring to the same common time here, they are not independent. However, what can happen, see, like if only one person wins in week 1, it's either you or Vanessa, it can't be both of you. And so in A and C, you can have one person winning in week 1 and one person in week 2. And these are independent since they refer to different weeks here. Another example is answering different questions. So event A is this person selected to answer 1 question, and B is selected to answer question 2. So A and B are different random circumstances, but are they independent? And so I believe this refers to an earlier example, but essentially here, if you're pulling a name out of a bag and there's 50 names, then you have a 1 out of 50 chance. But when they remove that name from that, you cannot select it anymore. And so it would be 0 because she couldn't answer this question again. That would be like if I was going to ask one of you guys a question here, and I have all your names down, and I pick one out, and I say, Annie, answer the question. And so when she asks a question, I'll put it to this side, then I'll pull out another question and ask another student a question, and then Annie cannot answer that second question because her name's already over here. She doesn't have a chance to do it. So in this case, knowing what happens in event A changes what can happen for your probability in event B. So A and B are not independent here. And this kind of brings into the idea of conditional probability. So regardless of whether event A has occurred or not, if you don't replace that first card, so we're talking about these types of events here, is drawing a 5 from a 52 card deck. If you don't replace that card, then they're not independent, because if you know that there's less than a 5 in the deck, you can play differently. It's like the idea of counting cards in blackjack. You know, in blackjack, you can use, essentially, if you get 21 points or score, then you get a blackjack and you win, and if you go over, you don't want to go over and you immediately lose. And so in this case, if you know that cards have already been drawn from the deck, you can keep track of that in your head and know that the event of you winning is higher or lower depending on what has already been played. And so when you calculate the probability for dependent events, that's what we call conditional probability. And so the different conditional probability, I believe it's on the next slide. No, we have it here. So conditional probability is the chance of B occurred giving the chance of A. And so we use this little line to represent knowing information about A. So if we know about A already, then that will help influence the probability on B. And so in this case, if I have the probability of B, which is selecting a 5 from a 52 card deck, and A was already a 5 that you drew, this would be this probability right here, 3 out of 51. And then the probability of B, if A is a not a 5, because we don't really care what other card is in this case, then this would be 4 out of 51 if you didn't replace it. And so if the two events are independent, A and B, then the probability of A multiplied by the probability of B is the probability of A and B. I know I'm saying the word probability a lot, and I will be for this class and next. All right. So another example here. So the probability that a teenage gambles differs for boys and girls. And so let me go through this here. All right. And so we have just a large number of students fill out a survey of whether they have gambled or not between 9th and 12th graders. And so the proportion of males and females, they admitted they gambled at least once a week during the previous year they reported. So just for the 9th grade here, you can talk about any subset of your data set. But the conditional probability here is the probability that, gambles, and I'll have that weekly here. It depends on whether you have a boy, which is 0.229, and the probability of gambles given girl is 0.045. And so in this case, I might multiply out the probabilities and find out the probability of gambling in 9th grade overall might be 0.18. And this number doesn't exactly reflect everyone. It depends, your probability of gambling depends on if you're a boy or a girl. If you're a boy, then you're more likely to gamble, much more so than if you're a girl in this case. And so the dependence in this case is on the sex of the student. And so if you know about the sex, you can make a good inference on whether they will gamble during the week. Right. Another rule we have here is the multiplication rule. And so I'll just have all this up right here. But essentially, we talked about a little bit the multiplication rule here, but this is only in independent events. So generally, we can have a multiplication rule, and I'll get this up here. We have the probability of A and B is the same thing as this. If I refer to the probability of A or B, I'm talking about this. And I'll do this in blue up here to reflect what I'm talking about. And so just in mathematical notation, a big, how like a St. Louis arch or something, refers to as and then the big U refers to union, which is or. So if I talk about, I have a word problem, and I talk about the probability of A and B compared to A or B, you have different ways of calculating this. And so if we think about it in the Venn diagram way, this up here, we have the sample space as here, and suppose we have two events, A and B. So just from looking at this, we automatically know that A and B are not independent since they have overlapping space in here. And so if I was talking about the probability of A and B, I'm referring to this space in here, this common blue space. And the way to calculate that is if you take the probability of A plus probability of B minus the intersection white on side. That's for you. Sorry. And so the probability in one statistical trial that both A and B events occur at one time. And so if they're dependent on one another, the probability of A and B is the probability of A times the probability of B given A. And the same thing for the other way around, you can change around the events and they're still the same thing. And then if they're independent, then they're just multiplied by one another, since if A and B be independent, then the probability of B given A is the same thing as the probability of B, and the probability of A given B is the same thing as the probability of A. And so you can see in this case that if they're independent, you would just plug this in up here, and it would just be probability of A multiplied by probability of B. So just one small, I'll leave this up here for a second, and then we'll get to the example. All right. So suppose our example talks about roommate compatibility. So this one person, Britt, is off to college, and there's 1,000 male students, but he knows out of all these 1,000 who likes to party, doesn't like to party, snores, and doesn't snore. And so in this case, we're talking about event A, which is talking about that they like to party. And so the ones who like to party are referring to this 250 that's all the way the total of all the people between snoring and not snoring is 250. And since we know that there's 1,000 male students, we can just do the amount of times it occurs, which is 250, over the total number of trials, total number of students here, which is 1,000. And then we have the probability of snoring, where that's the 350, and the probability of B, which is 350 over 1,000, is 0.35. And so suppose we want to figure out the probability that you'll be assigned a roommate. They either like to party or snore, meaning both events. And so in this case, it's probability of A or B. And so what we're referring to is all of this Venn diagram space right here. So all of where the black circles are is what is A or B. You can have A, you can have A and B, or you can have B. And so what you could do, what you have here, is that you have the probability of A, which is 0.25, figured out there, and you have probability of B, which is 0.15. And then you can look at the table to see, okay, who likes to party and snore. So it's 150, 150 over 1,000 is 0.15, and that's 0.45. And so if you don't want a roommate that likes to party and snores, or snores at all, you have a 0.55 chance of getting that roommate. And the last example we'll go through today is talking about probability of either 2 boys or 2 girls in 2 bursts. So what we have here is the probability that a woman who has 2 children has either 2 girls or 2 boys. And so in this case, the probability of a boy having birth, probability of birth boy is 0.512. Probability girl is 0.48. And so if the event A is 2 girls and that they're independent, we can use this formula right here to just solve what the probability of having 2 girls is and 2 boys. So the probability of 2 girls is the same thing as probability of 1 girl times the probability of 1 girl. They're not influencing one another, and this is just 0.2381, and the probability of 2 boy is the same thing here. Probability of 1 boy times the same again. For the math that's on the slide, 2621. And so we call these 2 events mutually exclusive. You can't have and 2 children, you can't have 2 girls and 2 boys here, at least in this example. And so the probability you either have 2 girls or 2 boys is just them added together, since there's nothing in common between these 2 events. The probability of 2 girls and 2 boys is 0. So then all you have to do is add these 2 together, and then you get around 0.5. All right. Well, that's the end. Does anybody have any more questions about this? Well, if not, I will stop recording. Free to go.
That's what I feel bad about. I feel like I always get texted before I left home and like sit distracted and do other things. I start looking at the Jeopardy desk like, what am I doing now?
I don't, one of my friends went out.
Yeah, that's fine. I'll send it on the slide.
So I can't decide if I'm gonna stay or vacation.
Is it that weekend? Isn't it like Halloween? Yeah, Halloween. I'm having fun.
I know.
It won't be good. Thank you guys. Thank you. Yeah, it'll be due at least Wednesday next week or so.
Perfect. Thank you.